Hey, it's Dr. J. Today we're going to continue discussing limits, in particular the calculus definition of continuity, or what it means to be continuous. Intuitively, continuity can be thought of like cursive writing. In other words, if you can write it or draw it, we're going to be doing some graphing today, without lifting your pen off the surface, that's an intuitive understanding of what it means to be continuous. So let me try this. I wrote this before we started the video. Let me try it live here. See if I can write the word continuity without lifting my pen. Let's see. All right, that's the best I could do without lifting my pen. So notice even cursive writing is not always continuous. It's very difficult to cross your T's or to dot your I's without lifting your pen. Another problem is that we always start with a function. And this is calculus. And calculus, at least this level of calculus, requires that we have a function in order to discuss anything, in particular to discuss a limit, which we've been talking about for the last couple weeks. And so you notice that not only do you have to lift your pen in order to write the word continuity, it's also not a function. So let me go back and show you what the word continuity would look like if it was actually a continuous function. Well, you can't have the letter C because that does not pass the vertical line test. So that's about as close to the letter C as you can get. You also can't have the letter O, because the letter O is not functional. Now you can kind of have the top half of the letter O. Well, I guess you can't even have that because it's connected to the N there. So the rest of this is all functional. It's getting a little sketchy in here. I can't have any actual vertical lines, but as long as these aren't vertical, it's okay. And then you definitely can't have the letter Y, because if it, doubles back on itself like this, it would not be a function. So that's about it. This is what the word continuity would look like if we were giving it a calculus definition or even an algebra definition of a function. So we're going to need a better definition, right? I mean, intuitively, you can think about it as continuous means you can draw it without lifting your pen. But we need a calculus definition, and then we'll see some pictures of it. So let's go ahead and start with an example. This is the key example that I really like to refer to when I'm talking about what it means to be continuous. It's not the only example, but it's certainly a very simple example that will help us understand this. So we have a function, f of x equals x squared minus 1. And since this is calculus and we're taking limits, let's take the limit as x approaches 1. It's a nice refresher of what we did in a previous section. So the way we handled this, now why did I pick 1? Well, I hope it's obvious. I picked 1 because 1 is the number that causes this to become 0 divided by 0. It's one of those indeterminate forms. And so the way we handled this was by dividing the factors. So we factor the numerator, we factor the denominator, and dividing, also known as canceling. And so now we have the limit as x approaches 1 of x plus 1. Yeah, I'm going to go ahead and keep the parentheses on there just to make it clear. Now here's the problem with this. You can now calculate the limit, all right? So that's nice. You can just plug in 1 and you can say that the limit is equal to 2. So over here on my graph, I got x equals 1, and then I got my y value 2. I know that the limit is equal to 1. However, the limit equals 1 the limit is equal to 2. The limit as x approaches 1 is equal to 2. But the limit tells you what it's getting close to. It doesn't tell us what the actual value of the function is there. So I need to make a very important distinction. You always want to look at the original function. F of 1 is not defined. In other words, x cannot equal 1. Now, sometimes in a good, well-defined function where the domain is given in the problem, you'll often see this notation off to the side, but it's not always directly given to you. This is sometimes implied by the nature of the function. Right? So if I wanted to be extra clear, I would have said f of x equals x squared minus 1 over x minus 1, where x is not equal to 1. I'm just making it abundantly clear that the function is not defined at 1. Right? You cannot plug 1 into this function. So this is not really f. This is not really f. Like, you can't see that. I'll put it over here. F is not really x plus 1. So x plus 1 is a representative of f everywhere except at 1. So it's interesting. The function x plus 1 looks like this. So let's call this g. It's a cousin of f. It's a close relative of f. So this is what the function x plus 1 actually looks like. Yeah. But the function in this example is not actually g. It's f. And so f looks like this function, x squared minus 1 over x minus 1. So what does f actually look like? Well, it looks just like g, except for it has a hole, also known as a removable discontinuity. This is what f looks like. So what's the moral of this? Well, if you simplify a function using algebra, and then you evaluate a limit of the simplified function, you're getting the value of the limit correctly. That is true that the limit is in fact 2, but you are not getting an actual dot at 2. You're getting a hole or a removable discontinuity, which is, again, bringing us to the topic of today's lesson. So let's discuss the continuity of this function at x equals 1. So this is what we call the pointwise continuity definition. A function is continuous maybe I should name the function. I'll just give all my functions today the same name, f of x, at x equals a, if, And then there's three things that have to be true. So all three of these things must be true. One, f of a must be defined. So you can't have a hole, right? Well, you can have a hole, but the hole better have a dot inside of it. So this would what it means to be defined, which would mean that the hole was actually filled in. So you can have a hole for a second, but at some point that hole better be filled in. So in other words, there must be a value defined at A. All right. The next thing, the limit must exist. Now we're talking about A, so we'll do the limit of f of x must exist. And again, when I say exist, I mean the left hand and the right hand limits agree with each other and they give you the same value. I'm not going to write all of that out because now we've had a very detailed exposition of what limits are. So every time I say that the limit exists, I mean it's a real number. Yeah, it's one particular real number. And then finally, the third thing is that number 1 and number 2 must be equal to each other. So this is the definition of what it means for a function to be continuous. So in example 1, is not continuous. You can also say discontinuous, but I'll just say not continuous. It means the same thing. At x equals 1, because, so I will ask you what rule is violated. Rule number 1 was violated. Notice rule number 2 was okay, not violated. Yeah, the limit does exist. It's 2. Yeah. Rule number 3 is also violated, but I usually go in order. So which one of these was first violated? So if this rule is first violated, then there's no point in even checking the other rules. Clearly, by the time you get to rule number 3 is violated if rule number 1 isn't defined, right? Because you can't have so they're kind of progressive. You first have to have a definition of what it means to plug in A. Then you have to have a limit existing. And then finally, the first 2 things must be true in order for the third thing to be true. Okay, so that is the formal definition of continuity at a point. And I will often ask you to tell me whether or not a function is continuous, again, at a particular value, and then tell me which of the rules are violated. It takes a lot of time to use specific functions. We'll get back to that in just a minute. Let's just run through this definition very quickly with a couple more graphs that are sort of pre-made for you. So example 2, given the graph of the function, as shown in the graph, tell me which of these rules is first violated. Which rule of continuity is first violated at x equals 3. All right, so let's see a function that's violated. So something like that. All right. So let's go through them one by one. So we're looking here at x equals 3. Is f of a defined? Yes. Yeah. F of 3 is equal to 1. So it is defined. There's a solid dot at 3. Does the limit exist? No. So it's rule number 2 that is first violated. We don't even bother looking at rule number 3 because rule number 3 only applies if both rule number 1 and rule number 2 are satisfied. So rule number 1 was satisfied, check. It is defined, but the limits don't exist. Yeah, the limit from the left is 4. I didn't write that very well, but you know what I mean, right? I mean, the left-hand limit, it's got a little minus sign up there. And the limit from the right, might as well review all of this. It's going to be on the test, is 1. And so this rule is the first one that's violated. One more of these, just sort of running through the rule, and then I'll erase the rules here, and we will get into some more detailed graphing, which you might have to do on your own and not have me draw every graph for you. I should mention that in this course, every time I draw a graph, you should, on your own, be able to reproduce that same type of graph. I don't always require that. I sometimes, give you free graphs, mainly because I'm trying to teach calculus and not teaching graphing so much. But, in the course of teaching calculus, some refreshers from algebra of graphing might be very useful. Let's say what's violated at -1. So over here at -1, we have a function, and it looks like this. So there's our function. Example 3. Same thing, given the graph of the function, shown in the graph, which rule is first violated at -1? All right, so rule number 1, f is defined. F of a is defined, yes. So this one's not violated. F of -1 is -2. Oh, no, it's not. It's +2. Sorry. I was looking at the wrong spot. So again, define means the solid dot. That's what it means to be defined. The limit exists. Now say -2. Yes, the limit as x goes to -1 is -2. That's the limit. So the limit is -2 as x approaches -1. The definition of the function is +2 at that point. And so it's rule number 3 that's first violated. So it survived the first 2, we call this continuity tests. There are 3 continuity tests, and we usually do them in this order because if it violates the first one, there's no point in even checking the next 2. Yeah, it's like a driving test, right? Although there's not 3 driving tests, but if there were, if you fail the first one, you don't get to take the second one, right? Or the third one. If maybe they should have a third one. Maybe not. I don't know. All right, so that's it for the basic definition. We got a lot to cover today, so I should shut up and start doing some more detailed examples. In other words, ones where the graph is not so obvious. So instead of saying given the graph, I'm going to say graph. So graph the function. And we're going to also see a new type of function today. It's called a piecewise function. We'll start off with two pieces. So this is what we call a piecewise function. It essentially means it looks a lot like the graphs I just drew. There are two distinct pieces, and we want to draw them to determine if it's continuous or not. Okay. The critical value is 2, so this is the A. So that's where we're going to be focusing our attention. We call that the critical value. All right, you all know your inequalities, right? So this is what's called an open inequality. So this will be the whole, sometimes referred to as open. And then this will be a dot, also known as closed. All right, so we say hollow and solid, open and closed, whole and dot, yeah, or point. It's really what a dot is a point. All right. Now remember, this is not only is it a hole, but it's also a line. Yeah. So we have a line with a hole at the end of it. All right. So what we do is we plug in to find the hole. So we plug in 2 into where the X is, and we find the hole. So the hole is at 2, 6. 1, 2, 3, 4, 5, 6. Oh. 1, 2, 3, 4. I'm not going to make it to 6, so we're going to have to use a stretched out scale or a compressed scale. 1, 2, 3, 4, 5, 6. I changed my mind. If you're taking notes, just back up a little bit. I'm compressing my scale so that 2 is here and 6 is here. Now be careful, this is not a dot, this is a hole at 2, 6. Sometimes what I'll do is I'll put a hole around it to remind myself that that point doesn't actually exist because it's open. All right. And now I'm going to plug in, so maybe I'll be a little bit more clear about it. This will be called the left piece. So X was 2, put a hole around it. Y was 6. All right. Now I'm going to plug in a point less than 2 because it says X is less than 2. So let's go with 0. You only need 2 points. I can do this with mental math. 0 plus 4 is 4. That is a solid point because it's to the left of the hole. So this is what your graph looks like. It goes right off the screen like that. That's the left piece. That's the line. Let's do the same thing with the right piece. The right piece will be a parabola. You can just call it a curve for now. But you know from algebra that x squared is a parabola. And it will have a dot at 2. All right. Sometimes I'll put a solid dot like that right there just to remind you. It's not a decimal point. It's a solid dot. I have tried doing this, but look what happens when I do that. You can't see the 2. So that's a solid dot at 2. Now we're going to plug 2 into this function here. So we got negative 2 squared plus 4 times 2 plus 2, which equals negative 4 plus 8 plus 2, which equals 6. Nice. If these agree with each other, that means it's going to be continuous. So I already know it's going to be continuous. So what happens here is this fills in the hole with a solid dot, and I need one more point, anything greater than 2. All right, let's try 4. If you want, you could do 3, but it's a little tight here, so I'm going to go over to 4 to make more room. I'm really running out of room, so I'm going to recycle my old one here. So that's going to be 16. Now be careful, the negative stays outside of the parentheses, so it's not negative 4 squared, because that would be positive 16. It's negative, wait for it, 4 squared, right? That's different than negative 4 squared. So this is negative 16, that's positive 16, so that's going to be 0 plus 2 is 2. So I've got 4 and 2, so right about there. So there's your parabola. All right, so we have a line, we have a parabola. You don't see the arrow tip. It'll just go right off the screen like that. But this is a half parabola. When you're graphing these on your computer for the line, you're going to use the tool that looks like kind of looks like that. I don't know if you can see that very well. So that's what the tool for the line looks like. It's cut off. And then for the parabola, you're going to use the tool that kind of looks like this. All right, and you just draw it with your mouse. I may film a supplemental video that kind of just shows me drawing these with the mouse. I think that might be helpful. I don't want to break into that right now. It would require me stopping my video and bringing up another screen. So stay tuned if you have any trouble with the graphing. I think this course probably could use a little refresher on how to draw with the mouse. Unless you just took my Math 10 college algebra class, you saw a lot of the same type of graphing. All right, so it is continuous. So the function f is continuous at x equals 2. We also have the limits. The limit as x approaches 2 from the left is 6. The limit as x approaches 2 from the right is also 6. Because these both agree with each other, that means that the limit generally is also 6. Right? So again, if these have to agree with each other, they have to give you the same value, and then that means the limit exists. Right? So remember, in order for a limit to exist, there has to be 2 limits that actually agree with each other. And the function exists. It's defined. F of 2 is defined, and it's defined to be 6. So check, check, check. Everything checks out. So it is in fact continuous. All right, so that's how you're going to do these graphs. For now, at the beginning, I like to do a combination of a line and a parabola, or a half parabola and a half line, I guess. We might do some more fancy ones at the end of this video. For the rest of the examples today, I want to show you what it, well, maybe not for the rest, but I would like to be able to do these blindly, like without actually looking at the graph. All right. If this is not continuous, it should be pretty obvious. Yeah, these limits will not be equal to the same thing, and then you will say it's not continuous. We'll see more of that, but in order to expedite the process and keep this video at a reasonable lecture length, I'm going to move on to what we call the blind examples, which means we don't see the graph, but we can understand what it looks like without actually seeing the shape. All right, example 5. So we have a piecewise function, and a whole bunch of these today. In fact, looking at my notes, I think they're all piecewise functions. It's really the most effective way to talk about continuity is by looking at a function that has multiple pieces. So let's try 2 lines. So we have 2x minus 1 and negative 2x plus 7. Sometimes I'll say if, sometimes I'll say for. Sometimes I'll say when. Oh, it's 2 again. That's okay. It makes for a good example. So sometimes we don't write a word at all. We just put a comma or a colon or a semicolon. There's really no standard, believe it or not. You have to put something, something to indicate that this is the condition under which this is true. All right, so is this continuous at 2? Yes or no? Well, how are you going to do it? Well, you have to first say, is f of 2 defined? So this is sort of the big question that we're asking. And so in order to do it, we're going to go through the 3 rules. Yeah. Is it defined? Well, yes, it is defined. Yeah, this is what this means. Yeah, greater than or equal to. In the old days, they used to actually write it this way. Greater than or equal to. And so these symbols have morphed together over time to become this symbol, greater than or equal to. So yes, it's defined. F of 2, you use the second piece. And you get 3. All right, so yeah, it satisfies that. Let's do the second one. Does the limit as x approaches 2 of f of x exist? Well, I don't know. I got to do it from the left and from the right. So let's do the left. So this will be the left. I usually put the left piece first, but don't get too comfortable with that because sometimes you'll have 3 or 4 of them where the left piece comes first and then all of a sudden it'll switch. So make sure you read it carefully. I try to be consistent, but every once in a while I break consistency to make sure that I'm still awake and paying attention. Or make sure you're still awake and paying attention. So the limit as we approach 2 from the left is 2 times 2 minus 1, which is 4 minus 1, which is equal to 3. So far, so good. Yeah. The limit from the right. All right, so on the right-hand side, it's going to be negative 2 times 2 plus 7, which also equals 3. By the way, we already did that here. Check, check. Yes, it exists. And then finally, rule number 3, does the limit equal f of 2? Yes. Yeah. The limit is 3, and the function is 3. So is f continuous at x equals 2? Yes. The function is continuous at 2. Now, I said I was doing that blindly, but now that you see everything without breaking out my graph paper, it would sort of look like this. This would be x equals 2. This would be y equals 3. There would be an open hole on the left, and then there'd be a solid dot on the right, and the hole and the dot would match up with each other, and that would be the continuous function. Kind of looks like an absolute value function, right? Very, very similar to an absolute value. In fact, it is an absolute value function. We might see that later. All right, let's do more of these. I never know if it's going to be yes or no. I have a kind of a mixture of them. When I do one that's yes, the same, almost exactly the same question could end up being a no. So you want to make sure you go through all the steps. Negative 2x minus 6. I'll use a comma this time. All right, so is f continuous at x equals negative 4? No. Yeah, look. None of these are equal to. These are what we call open or holes. Yeah, there's no or equal to. So f of negative 4 is not defined. It violates the very first rule. So the answer is no. Function is not continuous. I'm not even going to bother trying to graph it. In your mind, you can imagine what it looks like, though. It looks like a half of a line with a hole at the end of it, and then another half of a line with a hole at the end of it. And I don't even know if they match up or not, because it doesn't matter, because it's not defined. So whether or not they match really is, you can ignore that part. I don't think they do, though. I don't think they do. Oh, they actually do. As soon as I said I don't think they do. I'm terrible. I said I wasn't going to graph it, but I can't resist. It's another one of these things. So it's not defined. There's an open hole there, but they do actually match. They're both equal to positive 2. I just mentally, I looked at this and I thought, well, what number is that getting close to? As x approaches negative 4, this is getting close to 2. right? And then I thought, well, there's no way this one's going to be close to 2, but it is. It's actually not an absolute value, though, because this one's a little steeper. This one has a steeper slope than this side. So it's sort of a not symmetric upside down V shape where the two sides do not agree with each other. All right. Let's try another one. It's pretty much all we're doing in this lecture, so we might as well get as many of them done as we can. I'm kind of showing you all the different types of piecewise functions as well. So you can think of this as sort of a catalog of different types of piecewise functions. Here's another one with a parabola. My favorite way to say it is if. That's sort of the nice mathematical way to say it. So here's another way to define a piecewise function. Instead of using inequalities, you're using equal to or not equal to. Not equal to actually means two different inequalities. It means less than or greater than. I don't know why I said -5. It's definitely not -5. It's +5. These have to be the same number. Otherwise, it wouldn't make sense. So when I say not equal to 5, I mean to the left or to the right. And then there's a hole at 5. And I don't know what the corresponding value is. We're going to find that out next. All right, so is f continuous at x equals 5? That's our question. All right. The answer is, I don't know yet. Let's start with number 1. Is f of 5 defined? Yes. F of 5 is equal to 2 times 5 minus 12, which is equal to -2. So it is defined. All right. Does the limit exist? Well, I don't know. I'm going to find out, right? So let's do the left and the right. Now, interesting about this example, the left and the right both occur in the same piece. So I already know that these are going to be equal to each other. All right. The left and the right are equal to each other because they're both existing in the same piece. So I'm tending to think yes. Yeah. I mean, it's defined in the function that the left side and the right side both follow the same piece of the function. So let's find out what that is. That'll be 5 squared. That's piece 1 minus 8 times 5 plus 13. Sorry, my head's getting in the way. So that'll be 25 minus 40 plus 13. That'll be -15 plus 13, which is -2. All right. So the answer, yes, the function is continuous because it's defined, the limit exists, and I should just maybe write over here, and the limit is equal to the function. That's the final test. So it passes test 1, test 2, test 3. So yes, the function is continuous. This one's actually interesting. I'm not going to draw the entire thing, but I'm just going to describe it with words. Again, I like to call this blind. Just imagine what I'm describing. It looks like it's a line, but because it's a line, the second piece looks like a line. The first piece is clearly a parabola, but the second piece is a line that's defined only at one point. So it's not really a line, it's just a dot. So this is just a dot. So the first piece looks like a parabola with a hole in the middle. Yeah, that's the first piece. And then the dot fills in the hole. And so it looks like a parabola. It's a continuous parabola. Let's move on to a three-piece piecewise function. Now remember, I got a lot of yeses, but I mean, I have had a no or two. If you take the limit and the limit doesn't agree with the function, right, you get one number for the limit, you get another number for the value. That means there's a hole and a dot that don't match, and then you would just answer no, it's not continuous. You would also tell me why. I think I have formatted these to be multiple choice so you don't have to type an explanation, but it'd be nice if you could write an explanation. That's what I would like to see, but since we may never see each other in real life, just pick the right answer, and I hope that you are learning. All right, let's do a three-piece. Three-piece function. So we have a line. I seem to have used a lot of twos today. We have another line. It's a very boring line. And another line. So it's three lines. Oh, I guess a dot. That's a dot, not a line. So a line, a dot, and then another line. 11 minus 3x. All right, so we have a line with a hole. It's super important to sort of analyze as you go along, right? And again, I don't know what you see. I've been doing this for a long time, so as soon as I write it, I see it, right? Maybe it's helpful. Because this is only one value, this is just a dot or a point, solid. Yeah. And then we have another line with hole. Now, I'm not really getting into the geometry. Technically, it's called a ray, right? But that would be the geometry definition. We could just call it a half line or a truncated line. You're going to use the tool that looks like a line with a, like it got cut off. Again, it's called a ray. I guess I could be using the proper term. As soon as I call it a ray, though, watch, when I graph it, it could end up being a straight line anyway, but I don't know. Ray is the official name. And then dot is the official name for a dot is a point or a defined point. So one is f of 2 defined? Yes. It is defined. F of 2 is equal to 3. All right. When you see a number like this and there's no x's, it means that it's always equal to that number. That it's the output has already been predetermined. So it doesn't matter that this is 2. Right? This could have been any number. I might have to change it up in a minute and see if I get something besides 2. There's lots of 2s and 4s and 5s. I try to keep it close to home because this is, the introduction to the concept. As the semester goes on, I never know what the values are going to be. We might see a lot more surprises in the future, but today there's not a lot of surprises. All right, so how about the limit? The limit as x approaches 2 from the left. So that'll be this side. Yeah, less than 2, so that's the left side. Now again, even though it's less than 2, it's a whole, so I can plug in 2 to determine the coordinates of the whole. So I get 5. All right, how about the other side, the right side? So that'll be this side. Yeah, x is greater than 2, so that's the right side. So I use the other version of the function, 11 minus 3 times 2, which is 11 minus 6, which is also 5. So yes, the limit exists. It's equal to 5. Because these are equal to each other. And then finally, step number 3, or rule number 3, does the limit equal the function? Does this equal this? No. So therefore, the function is not continuous at x equals 5. Or you could say it's discontinuous. All right, and again, I said I wasn't going to graph these, but I'm just going to, they're so easy, I might as well. There's 5, there's 3, there's a dot at 3, but there's a line and another line, or a ray. So this is the left ray ending in a hole. The slope is 2, so it's going up. And then this slope is -3, so it's going down. The holes line up with each other, but the dot doesn't fill the hole. The dot's in the wrong place, so it's not continuous. All right, well, I only have 2 more examples, and then the rest is up to you. I don't want to do every single problem. I want to leave some things for you to explore, but I am showing you the basic outline of how you can get through all of these types of problems. So I got time for 2 more. The next one's relatively straightforward. So let's do, and again, I never know. I'm like planning these out in advance. I like to be somewhat surprised. I like to have there be some mystery. They all sort of follow a very similar model. All right, so again, I have a ray with hole. Again, on the left. So this will be my left side. Before I do any math, I like to analyze everything. This is equal to, so that's going to be a point. And it's a constant. It's not a variable point. It's, in this problem, that point is automatically defined to be -5. It's like it's predetermined. As opposed to a variable where, well, it would depend on what x is. So when I create these problems, I often have, x will change. You might not see -4 as your x. You could see -3, but it really wouldn't matter. That value is predetermined. Right? Of course, it was predetermined by me or by the random nature of the problem. And then on the right-hand side, I have another ray with hole. Not really much to do. I mean, I could just talk our way through it. You want to do the quick talk through before I write anything down? All right. Think about if you put -4 in here, you would get -12 plus 8. -12 plus 8 would be 4. Or it'd be -4, actually. This would be -5. So I'm already going to say no. Yeah. Might as well save some time. Why? Because well, let's go through the rules. 1, f of -4 is defined, so that's not the reason. Right, it is defined. F of -4 is -5. It might be rule number 2 or 3 that's violated. Let's see which one it is. I know it's not continuous, but I got to make sure I clearly say why. On the left, the limit was -4. Oh, and on the right, it's also -4. See? Look at the function is just x. Yeah. So it's still -4. So this exists. Yeah, so the limit exists. Right. So it's number 3 that's violated. The limit as x goes to -4 does not equal f of -4. This rule is violated. Rule number 3. This one looks almost exactly like example 8. It's a line, it's a hole, it's another line, but then the dot is not in the right place. The dot doesn't match up with the hole. I would say for this homework, this is a pretty common situation. So before I do the last example, sort of to summarize the possibilities, and I do have them random, so you never know which of these is going to happen in which order. I mean, I could predict, I think this one's going to be like this. One is that rule number 1 is not defined for discontinuity. All right, so that's one possibility where the point just literally is not defined. There is no value there. The second possibility is that the point is defined, so the first one is satisfied, but the limit doesn't exist. And again, it's the limit as x approaches a, and this is the value a. This is the x value a. And then the third possibility is the one we just saw several times, where the point is defined. So there is a dot. The limit does exist, but they don't agree with each other. So this would be the third possibility. So 1, 2, 3. The limit exists. The function is defined, but these are just not equal to each other. So those are the three ways in which something could not be continuous. To be continuous, that's funny. To be continuous, to be continued. To be continuous, none of these things can happen. You have a hole, you have another hole, so the two holes line up with each other. That's what it means for the limit to exist. And then not only is the function defined, but it's defined in just the right way so that when you plug in your A, it fills the hole exactly. My last example has two critical values. So if you get this far, that means you've completed your introduction to continuous or discontinuous functions. The subject is continuity, but in order to learn about continuity, we see a lot of discontinuity to see it. So this is one of my favorites, and we might see more of this in the future. In fact, we will see more of this in the future. One of my favorite types of functions. It has three pieces. And they're all defined using inequalities. So I got x is less than or equal to 5. Oh, -5. There's the -5 I was waiting for. The second piece, that's a parabola. The second piece is a line. This is sometimes called a sandwich inequality, or a sandwich interval, or a half open, half closed interval, so it'll have a hole on one side and a dot on the other. And then this is what we call a horizontal line. It's constant, but instead of being defined just for one particular value, it's defined for every value, in this case bigger than 4. All right, again, I'm sort of doing this blindly. I may have time to draw a detailed graph, but let's just get into the nitty-gritty of it. You have a parabola, or half a parabola. It's not an entire parabola. It's cut off at -5, but it does have a solid dot. So the limit as x approaches -5, well, that'll be this piece here. Now this time it's -5 squared, as opposed to -5 squared. So this is a double negative, which will be positive. Plus 10 times -5 minus 1, which is 25 minus 50 minus 1, -26. That's the limit as x approaches -5 from the left. That's our left limit, less than or equal to -5. All right. Now here, x is greater than 5, so this will be left. This is right. It's right of -5. You could also call this the middle, because it's between -5 and 4. But for the time being, it's to the right of -5. So on the right-hand side, the limit as x approaches -5 on the right, well, I use this piece of the function. You might be wondering, wow, this is just algebra, right? We're just plugging in numbers. Well, we're plugging in numbers because we're taking limits of of functions in which it's defined. We don't have any undefined values yet, right? So as long as you can plug in the number, then do it. Enjoy it, because you might not always be able to do it. So that one comes out to be 19, not 29, 19. So we got 15 plus 4 is 19. These do not agree with each other. So the limit does not exist. Right? Ooh, I haven't used DNE in a little while, right? In my last video, I resolved limits at infinity now could exist. Right? We can put an infinity symbol. I'm not saying that DNE has gone away for this course. We still have DNE. We're just using it a lot less now. Right? We're only using it when limits literally do not exist. This one goes to negative 26. This one goes to 19. Those do not agree with each other. Right? They're not infinity or negative infinity. They're just non-existent. They're two different real numbers. All right. So that means on the left and on the right, they don't match with each other. This one would be a dot or a point on the left, and this one would be a hole. And they would not match up with each other. You'd have the dot in one spot, you'd have the hole in the other spot, and the dot and the hole would not match up with each other. You know that. We've seen it before. I still have my grid if we need to bust it out. Let me just put this here for later. Negative 5, negative 26 is the dot. Negative 5, 19 is the hole. All right. Now let's go to the other point. So this is going to be the left of 4. And this one's going to be the right of 4. And again, the left side will have the dot and the right side will have the hole. Sometimes those change. Sometimes you don't. You got to look for the or equal to. That tells you where the dot will be. All right, so we got the limit as x goes to 4 from the left. All right, left. So left of 4, right, would be negative 3 times 4 plus 4, which would be negative 8. Yeah, negative 12 plus 4. The limit on the right, well, it's a constant function. It's always equal to negative 8. So that means the limit exists. So I can drop the left and right symbols and just say limit as x goes to 4 is negative 8. It exists. All right. So that means I have a solid dot at 4 comma negative 8. Dot and hole match up. Yeah. So one of them's the dot, the other one's the hole. All right, the dot was on the left-hand side, the hole was on the right-hand side, and they match up with each other, so the limit exists. All right, well, there's nothing left to do except draw a nice graph of this. I've got some pretty big numbers, so I'm going to have to stretch the values out. So my Y scale is going to be exaggerated. I'm going to have to cover up a lot of the graph, but you get the idea. All right, so for my Y scale, because I've got these large numbers, I'm just going to go like this, negative 26. Don't count the tick marks. It's not going to be to scale. All right. And then I'm going to do something like this and call that 19. All right, and then I'm going to do something like this and call it -8. So again, the y-axis is not to scale. I would need too big of a piece of paper. I will do the x-axis to scale, though. So 1, 2, 3, 4. 1, 2, 3, 4, 5, -5. All right, so we have a dot at -5 and -26. So down here, solid dot, and we have a parabola. It's pointing up because it's positive x squared, as opposed to if it was negative x squared or -5x squared or any negative number coefficient, then that would be upside down. Again, algebra, it's always around us. Then we have a hole at 19. That's the hole. It was a line. I know you can't really see it, but it's a -3x plus 4. So that would be a line, negative sloping line, kind of going like this, all the way down to -8. Where it would end with a dot. So -3x plus 4 starts at -5 and ends at +4. That's the middle, really. And then finally, a horizontal constant function would just be a horizontal line. And what you don't see is the hole, because the hole and the dot matched up with each other. So when a hole and a dot agree with each other, they come together and you don't see the hole anymore. You just see the dot. Okay. And so I would say not continuous at 5. At -5, continuous at 4, x equals 4. So that's the conclusion. Okay, we got one more piece coming in the coming soon. But until then, I'm Dr. Jordan, and I'll see you on the internet.